Our next problem is called set matrix zeros. And in this problem, we are given an m times n integer matrix called matrix. And if an element is 0, we have to set the entire row and column to zeros. And we have to do it in place. So for example, we have the central 0. So we have to make the second row and the second column in a matrix 3 times 3 to zeros. And as you can see here, we did that. In the second example, we have the 0 located at the first column, first row. So we have to make zeros all the elements that are inside the first column and inside the first row, which we do after the transformation. And our second 0 is in the first row. We already transformed all the numbers to zeros in the first row. The remaining work is to transform all the elements inside the last column to zeros, which we do here. The m and n are just matrix dimensions, and they can range from 1 to 200. And we have a normal distribution for the elements of the math matrix, ranging from the minimal integer to the maximum integer. Now, if we move, we also have some additional follow-ups. First is that's a straightforward solution using m times n space is probably a bad idea. That means that we would have to basically create the same dimension matrix as our input as additional space. We will try to do it in less space. So that's the second follow-up. Simple improvement uses m plus n space, but it's still not the best solution. And our desired solution uses constant space. So we will see how can we derive the constant space solution. So here we have an example, and this is the matrix from the second example from the problem statement. And as you can see, we have here additional data structure. These are basically just arrays, and they are of the same. So this array is of the same length as the number of columns, which is 4, and this is basically number of rows, which is 3 in our example. So to get the matrix, to get the desired matrix transformation, we will traverse the matrix, which is basically m times n time complexity. And if we see, for example, in the first column, so after we traverse like this, if we see a 0, that means that we have to mark the corresponding row and the column that has to be transformed. So for example, here we have, so this can be a Boolean, and the default value will be false. And you see that our first element is 0. So we have to transform, we have to say that our first row should be all zeros. And also our first column should be all zeros. Next, we go to the element 1, and in this case, it's not a 0 element. So we still have false here inside the second column. And also, we don't change the value for the first row because it's set to true. Then we move to number 2. We still keep the true. We do not overwrite the true value in the first row because we know we have to transform all the elements inside the first row to zeros. We just we keep basically the third value because in the input math matrix, it's not a 0, it's a non-zero value. So we just keep our false value in this additional array. And the last element, 0, so we have to put true here because we have to transform the last column as well. We have to transform all the elements in the last column to zeros as well. Now we move to the next row, and as you can see, there's no 0 elements in both of the rows, so this will remain false. We don't have to transform the second and the third row. And also these values here, these false value, will not be switch to true, because as you can see here, both of them don't contain they only contain non-zero elements. There's no zeros inside these two columns. Now we can use these data structures to control the transformation of the matrix. So basically, if we have true here, we will traverse this array, and if we have true here in our input matrix, we will transform the whole row to non-zeros, to zeros in this case. So because it's true, all of them will become zeros. Then we go to the second element in this controller array, and it's false. So we don't do anything with the second column. Same goes for the third column, and for the fourth column, we transform everything in the fourth column to zeros. We do the same then traversing this array. For each row, if this value is true, we transform all the values in the input matrix to zeros. Here is false, so we will just keep the values as they are, and so on. So in this case, we would have m plus n space complexity, because we have to create an array that's size of the number of columns, and also an array that's size of the number of rows. But the thing is, we want to reduce this to constant space. So in this case, as if you can notice that our first, and let me just quickly switch to another color here. Our first row and our first column can serve as these control arrays. And what I mean by that, we will use the input matrix, actually a part of it, the first row and the first column, to mark that a specific column or a specific row has to be transformed to zeros. And we will do the same transformation as we did here. So we will just, instead of using true and false, we will just put zeros inside the elements. So for example, here in the first row, all of them will become eventually zeros, because we have a zero inside as a first element. Example here. And the only thing that left to do here is to, before we use the first row and first column as the controller arrays, is we will traverse it, both the first column and first array, to check if there are zeros inside of it before we do the transformation, before we start to insert the zeros in specific columns or rows. And if we will just have two booleans, the first row has a zero, and the first column has a zero. So we can accordingly transform both the first row and the first column. So let's solve this problem using Java programming language. First, we will, just for readability purposes, we will define our dimensions, rows and columns. Then we will declare two booleans for tracking if our first row should also become zeroed, and if our first column should become zeroed, and that basically means that the first column or the first row contain zero themselves. Next, we will traverse through the first all the first row, and if there's any zero inside the first row, we will declare our zero first row. We will set it to true. The same goes for the columns. We will traverse our first column, and if there's a zero in the first column, we will just set the zero first column to true. By doing this, after we are done with traversing the matrix, we know that if the zero first row is equal to true, we know that we have to zero all the elements inside the first row. The same goes for the first column. If it's set to true, we know that we have to zero all the numbers that are inside the first column. Now we've traversed through the matrix, first iterating through rows. It's a standard double for loop, and checking if the current number um, at the coordinates I and j is equal to 0, and if it's equal to 0, we will set the corresponding row in the column. And we will do this by using our first column and first row. So for example, if we have a 0 element inside the second row, second column, we will set 0 to our second element inside our first row and our second element inside our first column, so that we know that we have to zero out all the elements that are inside the second column and second row, which we actually do inside our next two for loops. We traverse row by row, and for each row, we check in the first column if the value is equal to 0. If it's equal to 0, we have to transform the whole row to zeros. We do basically the same for the columns. We traverse by the columns, and for each inside each column, we check if inside our first row that we have a 0 value. If we have it, that position declares which column should be zeroed out. And the remaining thing to do is to check if our 0 first row is set to true, in which case we zero out the whole row. And if our 0 first column, if our first column is contains a 0, and if it does, we just zero out the whole column. In this case, we are using only the input matrix itself, so the space complexity is constant, while we have at the most traversal through matrix, which is basically the product of its dimensions when it comes to time complexity, which in this case is just m times n, where m is the number of rows and n is the number of columns.